Hello everyone, this chapter will talk about technical principles of Kafka.
After this course, we'll be able to know basic concepts, application scenarios, system architecture, and key processes of Kafka. First, let's take a look at the introduction to Kafka.
While in today's world, real-time information, aka message, is continuously getting generated by applications like business, social, or any other type, which typically includes user behavior data. Application performance tracing, activity data in the form of logs and event messages, and so on. So this kind of information needs easy ways to be reliably and quickly routed to multiple types of receivers. But most of the time, applications that are producing information and applications that are consuming this information are well apart and inaccessible to each other. So this leads to the redevelopment of information producers and consumers to provide an integration point between them. Therefore, we need a messaging system which is responsible for transferring data from one application to another, so the applications can focus on data but not worry about how to share it. For example, by a message broker such as Kafka. So Kafka is a distributed, publish-subscribe messaging system that can handle a high volume of data and enables you to pass messages from one endpoint to another. Here, publish-subscribe system means that messages are persisted in a topic. I'm going to explain this concept in detail later. Consumers can subscribe to one or more topic and consume all the messages in that topic. A real-life example is Dish TV, which publishes different channels like sports, movies, music, and so on, so anyone can subscribe to their own set of channels and get them whenever their subscribed channels are available. Compared with other components, Kafka is mainly designed with the following characteristics. First one is message persistence. While to derive the real value from big data, any kind of information loss cannot be afforded. Kafka is designed with O1 disk structures that provide constant time performance even with very large volumes of stored messages, which is in order of TB. So with Kafka, messages are persisted on disk as well as replicated within the cluster to prevent data loss. Second is high throughput. Keeping big data in mind, Kafka is designed to work on commodity hardware and to support millions of messages, reading or writing per second from multiple clients. Distributed processing, which is easy to understand, it supports messages partitioning over servers and distributing consumption over a cluster of consumer machines. And real-time processing, which means that messages produced by the producer threads should be immediately visible to the consumer threads. Well, this feature is critical to event-based system. Except for these features, Kafka also supports easy integration of clients from different platforms such as Java, PHP, Ruby, and Python. Kafka is suitable for both offline and online message consumption. In actual practice, Kafka can be used in many cases like Kafka is often used for operational monitoring data. This involves aggregating statistics from distributed applications to produce centralized feeds of operational data. It also can be used across an organization to collect logs from multiple services and make them available in a standard format to multiple consumers. Besides, it integrates very well with Apache Storm and Spark for real-time streaming data analysis, which infers to a process that popular frameworks such as Storm and Spark Streaming read data from a topic, process it, and write processed data to a new topic, where it becomes available for users and applications. Kafka's strong durability is also very useful in the context of stream processing. Then let's take a look at the positioning of Kafka in Fusion inside Hadoop. Kafka serves as a distributed, partitioned, replicated message publishing and subscription system that supports online and offline message processing, and it provides Java APIs for other components. Currently, Kafka is used in multiple components such as Streaming, Spark, and Flume. Okay, so we move to the next part, its architecture. Before going deep into the Kafka, you must aware of the main terminologies such as brokers, producers, and consumers. Take a look at this Kafka topology first. Producer is to publish messages to a Kafka broker, which could be page fields produced by web frontends, log servers, CPUs, or memory. Broker is a service instance in the Kafka cluster. A cluster contains one or more service instances. Kafka supports horizontal scaling, and with a large number of brokers, we can increase the cluster throughput. And consumer is just a client that reads messages from a Kafka broker. This is what I mentioned before, the publish-subscribe messaging system. A producer publishes messages to a broker in push mode, and a consumer subscribes and consumes messages from a broker in pull mode. Here, notice that Kafka uses Zookeeper to manage cluster configuration, elect a leader, and rebalance data when consumers change. We also have some other concepts like topic, partition, partition offset, consumer group, and so on, so let me explain them one by one. First one is topic. Topic is the category of messages published to the Kafka cluster. For example, take weather as a topic. Daily temperature information can be stored in this topic. In the figure, the boxes in blue are a Kafka topic, which can be interpreted as a queue. Inside of this queue, this little box is a message. Messages produced by producers are placed at the end of the topic one by one, and consumers read messages from left to right and use offsets to mark read locations. I'll explain what is offset later. Then topics are split into partitions. For each topic, Kafka keeps a minimum of one partition. Each such partition contains messages in an immutable ordered sequence. Why do we need partitions? Because the partition mechanism improves the Kafka throughput. How? The partitions of a topic are distributed on multiple nodes, so multiple producers and consumers can concurrently access these nodes to read and write messages of the topic. And the number of partitions in one topic can be set during topic creation. In the figure, we can see a concept called consumer group. Consumers can join a group by using the same group ID, and the maximum parallelism of a group, which infers to the number of consumers in the group, is determined by the number of partitions. What does it mean? Well, Kafka assigns the partitions of a topic to the consumer in a group, so that each partition is consumed by exactly one consumer in the group. Like this figure, in consumer group A, it has 2 consumers, and consumer group B has 4 consumers. There is no consumers of the same group to read data in the same partition, right? So I have to emphasize again that Kafka guarantees that a message is only ever read by a single consumer in the group. Then let's talk about the concept partition offset. Each message of a partition has a unique sequence ID called as offset. It's a long integer to uniquely identify a message, so consumers can use topics, partitions, and offset to check the message that he wants. In order to improve the fault tolerance of Kafka, it has the partition replication policy, which supports configuring the number of partition replicas by using configuration files. Replicas are nothing but backups of a partition. They are used to prevent data loss. Kafka has master and slave replicas. The master replica is called a leader, and the slave replica is called a follower. The replicas in synchronization are called in-sync replicas, aka ISR. Kafka uses the leader to implement partition read and write operations, which means that both consumers and producers read and write data from the leader, and neither of them interacts with followers. Followers only synchronize data. If a leader fails, one of the followers will take over services as the new leader. A follower that lags too much behind the failed leader in terms of data synchronization due to its own performance or network reasons cannot become the new leader. The leader server receives all requests, so to ensure the cluster performance, Kafka evenly distributes leaders in all instances. During data synchronization between partitions, the followers actually pull messages from the leader, which to be specific is to use only one thread called replica fetcher thread to copy data from the leader. And when a broker is started in Kafka, the replica management service, replica manager, is created to maintain the connection between replica fetcher thread and other brokers. The leader partitions of the follower partitions in the broker are distributed in other brokers, and then a replica fetcher thread is created for each of these brokers to synchronize partition data. During data replication between partitions, the follower pulls data from the leader and updates the state of high watermark, which is used to mark the latest message. When a follower partition changes and affects the broker to which the leader belongs, replica manager kills the replica fetcher thread or creates a new one. So briefly, Kafka has a replica manager to manage the connections between leader and the followers. Once a follower affects the broker to which the leader belongs, the replica manager will kill the connection. When the messages in a partition reach a certain amount, it's not easy to manage the messages. So Kafka splits a large partition file into multiple small files, which corresponds to directories in physics. This is easy for us to delete messages that already have been consumed, reduce the disk usage. A segment file is composed of 2 parts, an index file and a log file. These 2 files have one-to-one correspondence and they come in pairs. The file with suffix index and log indicate the index file and segment data file respectively. The index file is used to locate messages quickly. Actually, the storage layout of Kafka is quite simple. A topic partition has a logical log. Physically, a log is a group of segment files of the same size. When a producer delivers a message to a partition, the agent appends the message to the last segment file. Segment files are written to the hard disk after a certain period of time, or when the number of messages reaches a certain number. After the write is complete, messages are made public to consumers. There are multiple files in each partition, and when data is being written to a file, the other files in the partition can only be read. When a file is written for, a new file is created for write, and the current file can only be read. The new file is named with the offset from the first file. With index information, you can quickly locate messages. Sparse storage of index files greatly reduces the amount of space occupied by index metadata. Here, sparse storage means to selectively store parts of complete data. For example, when there are 100 messages, only the locations of message 1, 20, 40, 60, and 80 are recorded. To locate message 23, you can locate message 20 from the index, and with 3 messages offset, you can find the right one. For traditional message queues, consumed messages are usually deleted. However, in the Kafka cluster, all messages, no matter consumed or not, are reserved. Of course, these messages are not permanently reserved because of the limited disk space. Actually, it does not need to. So Kafka provides 2 policies to handle messages that are out of date: delete and compact. Besides, you can set some parameters for log cleanup. The log cleanup policy parameter is to choose the way of log cleanup, defaults to delete. And there are 2 other parameters. This one is used to set the number of hours to keep a log file before deleting it in hours. The default value is 168 hours. Logs will be cleaned beyond this time. And this parameter indicates the maximum size of the log for each partition before deleting it. Delete is easy to understand, so I don't explain anymore. As for compact, well, let's take a look. Log compaction ensures that Kafka will always retain at least the last known value for each message key within the log of data for a single topic partition. The idea is to selectively remove records where we have a more recent update with the same primary key. This way, the log is guaranteed to have at least the last state for each key. This figure shows the actual process of compacting a log segment. The upper part is the logical structure of a Kafka log, with the offset for each message. A message contains a key and a value. A key could have more than one values because messages will be updated. After compaction, only the messages with the latest values are remained for each key. For example, K1 has 3 messages whose values are V1, V3, and V4. So after compaction, only the latest message corresponds to K1 is reserved, which is the message whose value is V4. But how to know this message is the latest? Well, in Kafka, messages are stored in sequence. So message with the largest offset is the latest message. Here, one more thing to notice is that messages of the log after compaction retain the original offset assigned when they were first written. This means that the offset never changes. As I've mentioned earlier, all messages in Kafka will be persisted to disks and are backed up to prevent data loss. But how to guarantee the reliability during message delivery from producer to consumer? Kafka provides three kinds of message delivery guarantees. At most once, messages may be lost, but are never redelivered. At least once, messages are never lost, but may be redelivered. And exactly once, this is what people actually want. Each message is delivered once and only once. But unfortunately, exactly once is not available in Kafka currently. Messages are delivered in different modes to ensure reliability in different application scenarios. Here, synchronous delivery is highly available. It means that whenever the client writes a message, it will be sent to the broker. And asynchronous delivery means that messages are stored in buffer cache and transferred to broker when achieve certain amounts. This one is easy to cause data loss. We don't usually use it. Commonly, we use synchronous delivery with confirmation and synchronous replication. Kafka Cluster Mirroring is a cross-cluster data synchronization solution of Kafka. It's implemented through the built-in tool MirrorMaker. This figure describes how to synchronize the target Kafka cluster with the source cluster. These are two different clusters. During data synchronization, the consumer of MirrorMaker consumes data from the source cluster and then uses the built-in producer to send the data to the target cluster. Then let me introduce the reading and writing process of Kafka briefly. For writing process, the producer connects to any of the alive nodes and requests metadata about the leaders for the partitions of a topic. This allows the producer to put the message directly to the lead broker for the partition. Then, how does the read process of Kafka work? Let's take a look. For reading process, the consumer subscribes to the message consumption from a specific topic on the Kafka broker. The consumer then issues a fetch request to the lead broker to consume the message partition by specifying the message offset while the beginning position of the message offset. Therefore, the Kafka consumer works in the pull mode and always pulls all available messages after its current position in the Kafka log. While reading, or we can say subscribing, the consumer connects to any of the live nodes and requests metadata about the leaders for the partitions of a topic. This allows the consumer to communicate directly with the lead broker receiving the messages. So this chapter briefly introduces Kafka, including its basic concepts, application scenarios, system architecture, and key processes. Okay, that's all for Kafka. Thank you.